So today I'm going to explain a rather tricky question over here. So the question asks us to find a positive value k such that the equation has exactly two real roots. So typically when we do this kind of question, so for this way, I am trying to use the algebraic method. So when I do this, okay, so I identify that when I factorize x, this is already one root. So if there are exactly two real roots, that means the factor in the bracket will provide us with just one more root. That's the thinking, that there will be one more root here. Given that there's one real root here, then I would use the discriminant. The b squared minus 4ac should be equals to 0 since there's just one more real root, right? And then I proceed to solve and I get k equals to 0 or k equals to minus 4 over 9. So because this will become k 9k plus 4 equals to 0. Right, k equals to 0 is unacceptable because in minus b plus minus square root b squared minus 4ac, right, even if this is 0 but 2a, the a is 0, then the whole, you still don't get a root. If a is 0, then you don't get a root. But in this case, k is your a. So k equals to 0 cannot be accepted. So rejected. So this is also rejected because the question requires a positive value of k. That means I don't have an answer for this question. Right. Actually, this is not true. This is a very special question because in the case where 4k minus 1 equals to 0, we actually get a repeated root. So when 4k minus 1 equals to 0, k equals to 0.25 or 1 quarter. When we substitute 1 quarter as our k, what we get is 1 quarter x squared minus 5 over 4x plus 0 and x equals to 0. This actually gives us another exactly one real root. Okay, because actually this is actually two roots, but it is a repeated root with x, so it's counted as one root. You see, this is x, you can factorize another x, so you have 1 quarter x minus 5 over 4. This means that actually our thinking that there should be just one root coming from here is wrong. It means that it will not give us the case where actually there's two roots here, because in this case when k equals to 1 quarter, it's possible to get two roots, with one of the roots being 0, which is a repeated root with this. So overall, since there are two 0 repeated roots overall, and then one more root over here, and so overall there's only still two roots. So this is a very special case, so we cannot rely on this method. We cannot say that there's just one root over here, because there are two roots, just that one of the root is 0, a repeated root with this. Because it's a repeated root, we also say that there is only just two roots exactly two real roots overall, because x equals to 0 and x equals to 0 in this case does not constitute a new root. However, just looking at this, if we just solve using this part, this is actually two roots, 0 and the other root, right? So that's why 1 quarter is an exception. So how should we approach this question, right? The actual way to do this, well, maybe I shouldn't erase all this. Maybe I just I just create a new page. The actual way to do this is to x squared minus 5x plus 4. x over x squared minus 5x plus 4 equals to kx. So the actual way to do this is to graph. So let's say with x minus 4, x minus, we factorize out the denominator to get x minus 4, x minus 1, right, equals to kx. So this on the left hand side, I graph the graph on the left hand side. I have 1, 4, 1, 2 vertical asymptotes and 1 horizontal asymptote, y equals to 0. And the graph looks like when x approaches infinity, right, it's actually 0. So within, let's say if 2 minus 1 is positive, so maybe I use the help of a GC to graph this first. X squared minus 5x plus 4. So I shall graph this. Right. So when y equals to 0, what do I get? When y equals to 0, x is 0. So it comes here and come up. And here it comes. That's only. And here it comes. Something like this, right? And we know that, okay, kx plus, on the right hand side is kx plus 0, is actually a straight line with gradient k. So we imagine, okay, so if this line passes through the origin, then in order to have a positive gradient and only cuts one more time, that means this line, the tangent of the gradient of this line must be the gradient of the curve at the origin. That's why such that it won't cut itself one more time and cut here also. You only just touch this point without cutting here or here, without cutting here or here, or anywhere to the left or right of the curve. So because it's a tangent, you only touch this part of the curve at one point. So if it's a tangent, this graph has this line has gradient the same as the gradient of the curve at this point. So therefore, I do a gradient. I find the gradient of this at x equals to 0, the origin. So let's see what happens. So this one, I will use the quotient rule, keep the bottom and differentiate the top, minus the keep the top and differentiate the bottom over the square of the bottom, the denominator. So when I substitute x equals to 0 inside, right, then it becomes 4 over 16, which is 1/4, which gives us 0.25, right? That's the gradient of this tangent line, right, which cuts the curve twice, once here and once here, twice. So exactly 2 real roots, and therefore the k value that we have should be 0.25. The gradient of the line is the same as the gradient of the curve at the origin, touches it only once. So that's the explanation, that k equals to 0.25 is the solution to the question.